Cool. Well, hi everyone. As always, if you haven't already, remember to like and subscribe to this video. Pay attention till the end and you'll hear about our giveaway. But yeah, today what I'm going to talk about is some work with Fabian, and it's about these very deep hierarchical VAEs, and maybe a bit of an idea of how to interpret them, and specifically giving a bit of a multi-resolution idea, which is from more old school approximation theory with wavelets. So what will we get to today? Let's find out. So the very first thing is jump in at the deep end, as always, with what are these deep HVAEs? If you look at the papers for them, and I'll show them in the slides, they feel almost like these electrical circuits, the way that they're constructed. And they're a bit hard to get what's going on, but they seem to make very good samples of human faces. So we want to investigate that a little bit. So we'll go through the basic idea with them is that you'll have like the autoencoder, or the encoder part. It goes to some reference distribution that is easy to sample from. Then we decode back, and it just becomes very, very outrageous how they design those. So for current state of the art one, we'll go through the forward, backward, and in particular, they also introduced this hierarchical structure. So what that means is that your image might be like 256 by 256. You do a bit of encoding, then you do a downsample of the dimension. And that downsampling of the dimension part is what we found to be interesting, hasn't been investigated terribly much, and what's going to be mainly the section 2. So there it's going to be about this downsampling step. Can we relate it to something that is interpretable in some way? And we find that it has a nice relationship to wavelet bases, and in general, these UNets that have the structure of trying to optimize a reconstruction error by having this bottleneck that they call it. So you come down in dimensions, and then the bottleneck is the bottom of the U, then you come back up. What is that bottleneck exactly doing with the downsampling that we have? So I'll just go over as well that and its relationship to wavelets to see how we can intertwine the two. And then we get a feeling then, once we see how they're related, what the bottleneck structure in these UNets actually does for the regularization properties. The last part is we jump back to the VAE, and we're going to try and interpret exactly what these weird electrical cells are doing, and what can we sort of infer from our section 2 modeling. And what we find is we can get a little bit more of the properties of this beastly structure that they have, and we exploit that to get a bit of a computational gain. So let's get into it. For the first part, I just want to go over just the VDVAE setup. So what they'll do is you'll have some forward process, and this is the sort of coming down of the UNet, and that makes some latent variable Z. So Z will depend directly on your input data point X here, and from that Z, we sort of know more about it. So you'll know the Z or Q Z given X. And the thing on the right-hand side is, I'm sure everyone's seen it, is the lower bound that you sort of optimize to get your learned distribution P to make your data as likely as possible. they split this into two things. So they'll have two distributions here. I've incorrectly written the second one, but the training distribution, this Q, what that does is you get your data point, you encode it down the bottom, and then you try and come backwards with knowledge of this data point coming through the encoder. And this first term here, oh, why is it highlighting? Oh, okay, it's highlighting. The first term in that cost is what we'll call a reconstruction. So given the Z that's coming through the encoder, can we get back to X? And then you want to try and unlearn that dependency. So the P that I've written here for the sampling distribution, really that given Z shouldn't be there. You just want to be able to sample from X. So importantly, the reconstruction term up here, when we make this P of theta, given the Z to be Gaussian, you can rewrite it as like an L2 cost, which will be useful for later. So that's all I wanted to say there. But now it's the ghastly part of what they actually use. So somewhere along the lines, the U nets became N nets. And by that, I mean, they flipped it around for some reason. And they have these encoder blocks here. Let me just get so I can write. Where is it? Yeah, so here, this is the encoder part. And what you'll do is you grab your input data, comes through. We have each one of these forward blocks will be some neural network structure. And then it bottlenecks with dimension reductions every time. How did I draw that arrow? Okay. And the idea here is that with the forward part, we generate a sequence of variables X, where you just want to learn that you see the terminal X. So Q will see the end of the bottom path and try and figure out how to come backwards with these top-down blocks. And as you can see, they have a little picture here where the input and they try to reconstruct it. So after you do this, then the P, like I said, will just cut off the encoder part so you can just sample from whatever distribution you've made there. So how ghastly are these blocks? The forward ones are quite nice. So it's just some convolutions, but with a ResNet-like structure. So you have a skip connection in each one of these forward blocks here. And this is important for later because I'll just write it down. You can think of this as the X. Is it shapes or something? Bottom left.
You wrote something.
Oh, okay. Might just. Okay, that's sorry. Sketch. Okay, that's doing something. Yeah, so what you'll have here is like a X n plus. This writing is working. So the part that comes through here, if you think of this input as just labeled as xn, and this is your xn plus 1, you'll get xn plus 1 equals xn plus some function evaluated at xn. So you can think of that a bit as a forward Euler discretization of a differential equation stepping scheme, where this is your flux, essentially this function here. The backwards pass now, so it's sort of easy to forget things, but now coming back through the dimensions, it gets a lot more complicated. And what we have is you'll have some input that comes from the bend. And we learn two distributions. One gets to see something from the bottom up, which is this X variable that was coming down. The other doesn't get to see that. So this is sort of your reconstruction of I see X and I need to get back to it. P just sees the bottom of this here. And it's trying to learn how to connect the very simple low dimensional density to your actual data. So there's a thing in the cost to make these two as close as possible. So reconstruction with Q and sampling with P. And again, we get this sort of like resample step and resonate like structure. So here, what's predicted is the mean and variance of some Gaussian distribution that's added to our current input and then fed to the res block again. So for me, at least, that was pretty what's going on. I don't really get it. But what I find the most interesting part is this pooling step, which is the jumping between the dimensions. So what we've done here, or what they've done in their paper, ours is the next slide, is they've grabbed just a starting point here, and then used the reconstruction distribution for a certain part of the decoder, and then they've used the just sampling distribution P for the rest. So if you like, this has information of how to get back to X. This is just sort of going in some not straight on direction. And at the different block resolutions, if you sort of reconstruct for a longer amount of time, you get more and more detail on the background of these images. So I just want to point out particularly maybe the hair here. It's a little bit blurry, and it sharpens for the small scale features. But from the very beginning, you get the large scale feature of the face. So what's jumping out there is this idea that the hierarchy is approximating the large scale features of your data first. And then as you increase resolutions down this UNet, you fill in more and more of the details. So we have a lot more here that are, if your site's really, really good, you could see that you get more detail coming in. But an important thing that I wanted to note was with these multi-resolution approximations, if you stand far enough away from them, all the approximations at the very low level resolution look just as good as the high ones. So the principal idea is you want to be right far away when you make your approximation of an image. So away from this, I have on the next one a slide of just a multi-resolution decomposition of an image. So here, what I've done is taken a photo from the D squared celeb A data set and decomposed it into various multi-resolution approximation spaces. So what this means is if you do this experiment, actually, like this one I can see is quite different to that one. But if you walked a bit down the hallway, you wouldn't be able to tell the difference between the two. So this is in some ways, you've lost a lot of information because it's squared, like this would be 64 by 64, while this is 256 by 256. So you have a lot fewer parameters, but you're not losing much information. So I think now the hierarchical structure of these UNets is utilizing something very similar on this vein. So what is this dimension reduction of this pool that they call here and unpool? Well, it's average pooling. So what that means is that if you have 4 pixels like this, so grab this one, this one, this one, this one, and I wanted to go from a 4x4 image to a 2x2, you take the average of those pixel values. So if we think about the actual function space that is represented at different resolutions, it's sort of going, oh, well, the functions which are piecewise constant on different dyadic partitions of the unit square. So grayscale image is one of these guys where your color intensity is in something like 0 to 256. So that's all nice. But what's special about these VJs? Why can't I? Oh, there we go. So each one of these functions is bounded just on the unit square. So very easy. We can just say that they're also in L2. The other thing is that the V minus J by minus J space is just a Kronecker product of this because the geometry is a square. So 2 unit intervals will get you there. And the average pooling, if you take one of these functions, you can think of as this sort of integral over the larger area with the size, with the scaling in front. So I'm taking like, well, just the average, so the mean of these 4. So what's so special about doing this between these V minus J's? Well, these V minus J's are known to be, well, this one back here that I've listed is actually a Haar wavelet multi-resolution approximation space. So what that means is each one of the VJs obey this nesting property. If you take all of them, there's meant to be a Z there, you'll eventually recover the whole of L2 if you take the closure. And then if you take the intersection of all of them, you'll get a trivial function. So the only function that you can approximate with absolutely no pixels is just a flat black 0 image. If you have infinitely fine pixels, you can get any infinitely fine L2 function. And you get this sort of scale invariance of the basis for these spaces. So multiplication by dyadic number will land you into another V minus J, and translation will also land you in one by dyadic amount. So take this part of the image, move it around. You'll also still be in this approximation space. The neat thing about this is you can build orthonormal bases of L2 of these approximation spaces. And the complements within each one of the V minus J's makes a orthonormal partition of L2. So what I mean by that is take a V minus J, you know that what lives within it is V minus J plus 1. So the intersection, so what I can decompose here is my V minus J space into the lower resolution of it and some orthogonal complement. So think of this as image at resolution 256. I go down to 128, and this is the part that's like the finer details that's discarded. If I just do this recursively, I can grab my V0, which is just here, we'll think of it as my trivial 0 function. And on the compact 0, 1, I can get a complete partition where each one of these U's are orthonormal with respect to L2 of one another. So this is especially nice for just if you have a function and you want to split up its L2 norm in this multi-resolution way, you can project it into each one of these. The last part is once you know a basis for this V0, you can essentially figure out the basis for the rest of the VJs because of the scale and translation property that we had. So for this one, this is going to be mother and father wavelets, or what they're called. So this is like just one on our first unit square, a unit line, and then this one is like a step function across. So it's approximating those pixels. And then this is all the ones that you can yield from those two. Now, back to the pooling operation. If we think of our image, and it can be represented in two ways. You can have it as the pixel value as a matrix, if you like, and that's the intensity at every point. Or I can say it's in my nice V minus J approximation spaces. I'll represent it in this lovely orthonormal Haar basis that I have. I can then ask, pooling in my standard pixel basis, what does that correspond to when I move to the Haar wavelet basis? So what I've done here is this is the standard basis. I do my pooling. I'm going to go with my pi minus j down to my Haar wavelets here. Oh, sorry. No, I'm going to assume that I have my Haar wavelets, move back to the standard basis, do my pooling, come back down. What's this map? And it turns out that the average pooling, if you have n many wavelet or j many wavelets, and I'm moving to minus j plus 1, I actually just chop off a wavelet. The pooling just throws away some of the higher resolution wavelets. And because these are orthogonal, this pooling operation in L2 this way splits up the part that you throw away and the part that you keep in an orthogonal way. So the actual downsampling of this UNet has this very sort of nice multi-resolution, it's not just pooling, it's projection, L2 projection between these approximation spaces. So what can we do with that now? Well, we know that the average pooling moves between the L2 orthogonal spaces. The reconstruction error normally has some L2 representation. So what you might think of is compare your data point, you apply your encoder, do some pooling, unpool, apply the decoder back to your data point, take the difference L2, something like this. We should be able to get a nice decomposition with the hierarchical structure now that we know that we can split everything up in this nice L2 orthogonal way. So here's a very toy-ish example. If you have F, just Rn to Rn, B to Rn to Rn, and I assume that they're inverses of each other, a reconstruction error would just be finding theta so that these, this gives me my identity on my data as I wanted. The obvious problem here is that this is underdetermined straight away because B and F could just both be the identity. So no dimension reduction does nothing for you. So for a moment, I just want to think of if these are linear operators and they're acting on the same dimension space, that's again just trivial. I can represent the identity as a linear operator. But if I introduce this projection down, so think of data in j dimensions. Now I'm saying, oh, I need to forget some amount of it. Then I can do this procedure. So I apply my forward process, apply my projection, embed it back, sorry, to Vj, so I can apply backwards. And this difference in the inside brackets is my reconstruction error, but I'm just assuming these are linear here. So I get this, I can take the f off essentially and get this bound here. So the right-hand side will be my reconstruction error. This is sort of how much f is shrinking or increasing the norm of my data. But inside this bracket, I have the f and the b. I'm just assuming when they're on the same dimension that they're inverses. So it becomes this difference. But the projection and embed here are to something that's L2 orthogonal. So the I minus this is really projection onto the orthogonal subspace. So what I'm saying is something like the size of how f maps my data, the part that's thrown away into the orthogonal complement is bounded by my reconstruction. So by optimizing this to be small, because I want my reconstruction to be good, I'm saying the proportion that I throw away after applying f to my data into the orthogonal complement is very, very small. So the idea is that f will be learned to push as much information away from that orthogonal complement that I'm going to discard for my reconstruction. So what I think that I'm up to at the moment is if I have v minus j, and now I'm thinking of measures over v minus j, and these will be like transition kernels, if you like. So given a measure, it'll give me another measure, and these are again parameterized by some neural network. And I'm assuming that on the same dimension, these are just inverses of each other. What I've done is, because it's no longer linear, the denominator here won't be a nice operator bound like it would be here for the linear part. I think it will be, so I'm still checking on this, basically how much these, how much the f either shrinks or enlarges the first two moments of my measure in here. So what I'm saying now is I take my measure, my data, mu, I move it forward by fj, I look at the part of the samples that gets thrown into the orthogonal complement, divided by how much fj is resizing the variance essentially of my distribution. And this can be bounded by the Wasserstein 2 metric squared of doing the projection, coming back, and this. So this will have some coupling of the two measures here as Wasserstein metric. So it's definitely bounded above by a chosen coupling. So I'll choose the coupling that is, I'll just feed it through these little f and b's that can be like moving a data point corresponding to whatever these kernels are. So what I'm saying is my hierarchy structure is saying throw away higher order wavelets. It's trying to learn that. So if I jump back to that VDVAE nasty cell, within each one of the cell blocks, I can think of that forward pass as doing some forward Euler discretization of this ODE of the XT. So the X0 will be my data, it comes forward. And then once it gets to the end of my forward process, I assign it to my Z0, which will be my latent to come back. The resampling with the resonance structure gives you this sort of like ODE step here, but with some stochastic parts. So you'll get an SDE like this. But the question that I had, and isn't really stated at all in VDVAE, is what is this sort of target measure for Z0 or XT at the very end of the UNet? So grab our bound from before, because they're all orthogonal subspaces, I get a neat sum, and I'm just viewing these as the compositions of the projections. So I grab all my spaces and I sort of sequentially project into each one. So my reconstruction loss here. And what I'm learning, right, is I want to always throw away the orthogonal complement that's chucked at each sampling step. The issue with VDVE is that they don't stop at some V minus J that isn't V naught. They actually go all the way until you hit that I can only approximate the trivial function. So what they're connecting our data distribution to is, if I think of everything just my measure as a product measure across my J dimensions, is a delta mass at 0. So it's just sending everything to 0. And you can think of the forward part as being some flow that's grabbing my data and it's pulling it towards 0. And then Z as blowing that up, back up. So this is what I said. It's shrinking towards 0. But the nice part about shrinking towards 0 is if your data all lives at quite a high magnitude and it's been pulled in, I'm not sort of moving forward, backward at any point. I'm only traversing across space in essentially one direction. So their modeling, they have independent blocks. Each one of those resonets had its own individual parameterization. So that gives it like a t dependence in the continuous time. But I really shouldn't need that t dependence, because no matter what point of time I am, the position will tell me which way to go. So I should just not learn the t. That corresponds to essentially weight sharing in the neural network structure. So that's the parameter gain here. This is something that's also nice that we sort of looked at, which was with images, Fourier features normally give you a big gain, because the idea is essentially grab your data. A good basis for L2 is a Fourier basis, and then do your modeling with a Fourier basis because it's nicer. But because this architecture is already implicitly enforcing an L2 orthogonal basis of wavelets, you shouldn't expect much of a gain from this. And we didn't really see too much of a gain with Fourier features there. So what I've done is, across the forward part of the UNet, just plotted the norms of the data points coming through. And as we thought, they're getting shot down to 0 across each resolution. So it's sort of, and the variance is also shrinking between them, but it's wanting to, it's shooting down towards 0 there, and then on the backwards pass, it's coming back up and increasing as we thought would happen. But now, if we look at our parameter sharing, so they have the model that we grabbed without parameter sharing. This is sort of the closest competitor. They use 30 million-ish parameters. The weight sharing trick gets you down to 200,000 with, this is your cost essentially. You're not losing really any performance here. And then at very large scale sort of stuff, so 64 by 64 images, the weight sharing cuts your parameters about by half without any performance reduction either. So that was a nice little inference for that. And then thank you, everyone. Don't forget again to like, subscribe, visit our Patreon page. And this is a giveaway, so your chance to win $1 million. First 10,000 subs will get a free non-trivial 0 of the Riemann zeta function. So watch out for that. It could be you that gets a good one. And here are my references. Thank you.
So instead of using the R wavelet, could you come up with a new architecture that just basically goes beyond that?
Yeah, so that's what
would it be useful?
I think it would be useful in there's two ways that you can do it. Either you can go, I'm going to think of a better pooling operation to get some gain there, and an idea would be if your data is well represented in a better wavelet basis, the neural network shouldn't have to do as much work to sort of push away, or if you get good compression with a better wavelet basis, a lot of the mass will already be on far fewer of the wavelet coefficients. So I do think using something like whatever they use in JPEG will get you some gain. The other one is we actually never encoded the wavelets specifically. So could you figure out what dimension reduction tools they're using that works really well and what the corresponding inferred basis is? Because maybe there's a very good basis for specific data types through some engineering type downfalling that we don't know yet.
So another thing is like when you think of it, like when you do your analysis and so on, you think of the image as a kind of infinite dimensional function that you basically look at the finite resolution. People have been trying to model things directly in infinite dimension using this kind of NERF type model. I don't know if you're familiar with that. It's kind of functional representation of the data.
Oh, okay.
I was wondering, but it's become very popular, this kind of things, and people have been using actually in particular Emilian.
Oh, okay, yeah.
Okay. It's to say, look, you don't want to think of it as the image of collection of pixels. It's just like literally you would like to model directly the function on that you throw in the domain, so if you want to kind of evaluate the pixels. But what is super disturbing with what this kind of model is that somehow, it's really black box kind of MLP and stuff, and there's really kind of it's not clear really all the information about the kind of resolution of the image is stored in their network. It's a bit strange. I'm really wondering whether you couldn't use some kind of wavelet ideas to get a better kind of models for that, which kind of functional data. Have you thought of using something like that? Sorry if it's unclear, but
no. I was going to say the reason I was looking more at this was I wanted the infinite dimensional thing, but there are a lot of ways to get to infinity. So, and for most data, assuming some form of smoothness is a really bad assumption, like images discontinuous paths. What is seen sometimes as a good assumption is maybe there's a resolution trend in the resolution. So like if I see putting finer edges on my hair at a finer resolution, I want to put even finer ones, finer edges. So it was more, instead of throwing away each one of these orthogonal complement subspaces, can I model the relationship between them? So then there's something like some time-dependent model on the resolution on this decomposition. And that way, you sort of have some finite resolution, but then you infer to deeper resolution.
But isn't it somehow with Valentin does and wavelet stuff? It seems to be very related to what he's been doing. Because somehow he does stuff, a diffusion on coarse coefficient.
Yeah.
And then he imputes the finer detail conditional upon the coarse output.
Oh, yeah.
And he just kind of refine like it's kind of learning the. Is it related to what you're trying to do?
Yes, that would be. And the other one was I think I've shown it to you where they've made, it was in the 90s again, these infinite dimensional models of images. And if you get that modeling between the resolutions right, you can sort of just super resolution everything, and it works stupidly well. So I'm not sure why images do that, but yeah.
Any other question? No?
Cool. Yes, so am I. Thank you.